And Brown and LeMay deals with the early history of chemistry, and then also we start to talk about some of the basic things in chemistry. So this will be important to you. You'll want to try to make sure that you get this one really well because it's going to build a foundation for the rest of the class. Let's go to the next slide. So basically this chapter is going to be taken from Brown and LeMay and also from Zumdahl, a combination of those two. So Zumdahl's chemistry, Brown and LeMay's chemistry. So credit to those. And I think that's basically going to be it for this particular set of slides, these two sources here. Next slide. And as always, the commentary here is based on it's on my own commentary. A lot of the slide editing and changing up has been done by myself. Next slide. So three main things that we're going to be talking about in this chapter would be atomic structure, which we're going to learn a little bit about how they figured it out. A lot of this stuff happened around the turn of the 20th century. It's, for some reason, at that particular time, between about 1870, about maybe the time Maxwell was developing his equations for electricity and magnetism, all the way up through like about 1910, 1920. For some reason, there was just a whole lot of stuff that was discovered at that time. And then learning about the different kinds of bonds, the different ways that things are named. And we'll find that there are several different types of ways that we name chemical compounds. So let's go ahead and go to the next slide. So back in the early days of the Greeks, they tried to figure out how far down you could divide something. And they came up with the idea or the concept that if you kept dividing up, for example, an iron rod, smaller and smaller, eventually you're going to get down to some point where you've got as far as you can go. And they called that an atom. And that was pretty much prescient, because it turned out that they were right. However, they thought that these little things they called atoms were indivisible. And it turns out that that was wrong. But that was still excellent work on their part, as was a lot of the other stuff that they did. And then I'll let you read the stuff about alchemy and Robert Boyle on your own if you want to pause the video. I'm going to go to the next slide. Three important laws. Remember, we said that a law is something that people say, okay, this always happens the same way, like gravity. If you drop an apple, it's always going to fall down to the ground. And it doesn't necessarily mean that it's ever been proven or that anyone ever necessarily came up with the right equation to describe it. It just means that it's called a law because no one's ever observed any exceptions to it. So the law of conservation of mass turns out to be not correct. That law says that mass is neither created nor destroyed, but that's not true. But for all practical purposes, as far as we're concerned, it's true. It turns out that it is true if you include energy in it. So, I mean, I'm going to say this a whole lot. If you take me also in 1412, if you take my class, you'll hear me say this again and again, that mass and energy, work and energy are just two different forms of the same thing. And mass and energy are too. So mass and energy can go back and forth, and we'll talk about that a whole lot more later, but not right now. Going on to the next one here, the law of definite proportions. A given compound always contains exactly the same proportion of elements by mass. So, for example, for water, all the water is going to have 2 hydrogens for every oxygen, because the formula is H2O. He didn't necessarily understand that, at least not completely at that time, at the time that he made this a law, or wrote this law, but it's still true today. And then next slide. The law of multiple proportions says that, and this was by Dalton, says that when you form a compound from 2 elements, that the ratios will always be able to be reduced to small whole numbers. That means that anything from down to about 6 or less will be what you can reduce these to. So what that would be like if you look again at water. Water is H2O. So you have a ratio here of 2 hydrogens to 1 oxygen. Next slide. So Dalton's theory was kind of back to what the Greeks said Each element is made up of tiny particles called atoms. Let's go to the next slide. So we talked about this a little bit in the last chapter. So if you have an element, now when we say an element, we mean something out of the periodic chart. Again, remember we said there's about 100 things in the chart. Everything in the whole world that we know of anyway, and I'm pretty sure that's correct, is made up of one of those basically 100 elements. We talked last time about how some things that we think might be elements are really not, like brass. It isn't really an element, so you won't find brass or bronze in the chart because they're alloys, they're mixtures of elements. Things like water won't be found in the chart because water isn't an element, it's a compound, as we talked about last time. So Dalton is basically saying here that if you had a pure iron rod or a pure copper wire, every atom in that would be the same, which that's basically true in terms of the number of protons. And so there's something about copper that makes it different from iron. And without spending a lot of time on it right now, the thing that makes things different and the thing that makes things what they are is the number of protons. Okay, so that's so important and so subtle that I'll say it again. The thing that makes iron iron is the number of protons in the nucleus. And it's amazing and remarkable how much things change or can change if you just add one more proton. Just as one example, if you add one more proton to helium, it goes from being a very unreactive gas to being a very, very, very reactive metal, lithium. So what I mean is if you go from atomic number 2, if you look at the chart, up at the very top right, you see helium, and then at the next, all the way down the next row, number 3 is lithium. So the difference between lithium and helium is just one proton, but that one proton makes a gigantic difference. So different elements are different in some fundamental way. Let's go to the next slide. So when you have different elements, which means different atoms, they combine with each other to make compounds, or if we were looking at it in the macroscopic realm, we would say they were molecules. So again, back to our example with water. If you take 2 hydrogen atoms and combine them, and they're going to be covalent bonds, we'll learn about that later, with oxygen, then you get something called water, which is not an atom anymore, it's a molecule. So molecules are at least 2 different atoms. And they don't have to be different atoms. They can be 2 hydrogens, for example, would make a molecule of H2. Next slide. So chemical reactions involve reorganization of the atoms, the way that they're bound together. If you start off with water and do electrolysis of the water, you can produce H2 gas and O2 gas, which again we talked about before. So you're changing the chemical structure of the water from H2O and you're making it into H2 and O2, and that's not balanced, but it doesn't matter. So you're changing the not for right now. It will matter, but not right now. So you're changing the way that these atoms are organized. So that means you have a chemical reaction. So a reaction means that you're changing the chemical structure. Let's go to the next slide. Then we have a couple of more theories or whatever where people did experimental work. The volumes of gases and also the volumes of different gases at the same temperature and pressure. Avogadro actually found that the equal volumes of different gases contain the same number of particles, which, I mean, we don't want to just gloss over this. This is actually important, and we're going to come back to this in detail in Chapter 10. So this is a little bit weird and counterintuitive. If you think about it, if you have a certain amount of uranium, which is a huge atom, and you have the same amount of, let's just say, lithium, then you're going to have a lot more atoms of lithium in the same amount of mass. Like if you had, let's say you have 10 nanograms of each of them, you're going to have a lot more atoms of the lithium because it's much smaller. That's just common sense. But this is a little profound here. What we're saying at the bottom here is that it doesn't work that way for gases. It doesn't make any difference how big the gas molecule or atom is. So, I mean, it doesn't matter if you have H or H2 or H2O or CO2. CO2 has a mass of 44. and H2 has a mass of 2, but they still occupy the same volume. If they're at the same temperature and the same pressure, they'll occupy the same volume. Well, that's just plain weird, as they'd say on the Twilight Zone. So the reason is because it's not how big they are, it's how many particles you have. So this is different from solids and liquids. Let's go to the next gas. No, sorry, the next slide. I just woke up. Okay, so this characteristic is unique to gases, as we just said. So solids and liquids are not that way. So it does depend on how big the atoms are. So you see what I'm saying here? In a gas, it doesn't matter if it's a little tiny atom or if it's a big molecule, like a relatively big molecule like CO2, they're still going to occupy the same volume. The reason is because the volume in a gas isn't made up of the actual particles, it's made up of space. And so the particles bounce off of each other, and the volume that's occupied by the gas will be determined by how far apart these particles are. And because most of the volume of a gas is empty space, then it doesn't matter how big the particles are. Let's go to the next slide. Let's go on. You can pause this and read this if you want to. I'm going to go to the next slide. Okay, so let's get into some of the experimental work that was done around the turn of the 20th century. And as I've said several times in the past, in this class and other classes, there was a gigantic amount of work that was done around the year 1900, give or take. And why that happened that way, I think it has something to do with the fact that people at that time were beginning to combine their ideas across national borders. And then also the technology, the math at that time had reached the point where they understood calculus. And calculus is a very powerful tool in determining how things operate. Oh, excuse me. So anyway, in about this same era, J.J. Thomson discovered that if he took a glass tube, as you see here in your picture, and if he took everything out of it, and you can do it two different ways. You can take everything out of it and then attach electric potential across the two ends of this tube, then you can get something to go from one end to the other. And he was able to determine that in a different way, which we'll talk about in just a second. So in other words, what I'm saying is, first of all, if you just take this tube right here that I'm pointing at right now and evacuate it, and what that means is just pump everything out, which it was possible for them to do that. All the air gets pumped out, so there's a vacuum inside. And then you have a metal cap on each end, and if you attach those caps to like a battery and turn it on, then what will happen is that some kind of a ray will appear from one end and go across to the other end. And it was a very mysterious thing in those days. They called it a cathode ray. Excuse me. Which sounds like something out of science fiction. It turns out that we now know what that cathode ray was. Then there's another way you could do it, and that was, instead of just pumping out everything out of the glass tube, you could pump all the air out and replace it with something like argon. There's some kind of a noble gas. A noble gas is one of the gases in the far 8th column in the periodic chart. We'll talk about it later. And then if you put the noble gas in instead of the air, what would happen would be that when these cathode ray things would go across the tube, that they would hit those noble gas particles. And those were actually just atoms. They're not diatomic atoms or molecules, they're just atoms, like argon atoms. And when these electrons, as it turned out that the cathode ray was, when the electrons would hit the argon, they would cause the electrons in the argon to become excited. In other words, it was kind of like the electron would hit the argon atom and the energy of the electron would be transferred to the argon electrons. And that would cause them to go up into what's called an excited state. In other words, they would ordinarily be in what they call the ground state, where they're at a kind of a low energy level. But when they would get impacted by these incoming cathode rays or electrons, then that would cause these electrons to get bumped up to an excited state. But they don't stay in the excited state. They'll eventually come back down to the ground state, and that happens usually in a matter of just like nanoseconds. But when they come back down, then the energy that they had at the excited state has to be given off in some way, and the way that it's given off is by the emission of a light. So if you have a fluorescent light, that's the same thing that's going on is what we're talking about right now. So if you have a fluorescent light, you've got a long glass tube just like this one, and when you turn the light on, you're turning on the potential, and the potential will cause the electrons to start shooting across that gap, and inside that glass tube, they pumped the air out and replaced it with something like argon or neon. And so when those electrons impact those argons or neons, they cause the electrons in those atoms to become excited. And then when the electrons drop back down to their ground state, they emit light in the visible range. And we'll talk much more about that, especially in 1412 towards the end of the course, but also we'll talk about it also in this class. So that's how a fluorescent light works. Anyway, excuse me. Back to what Thomson did. Obviously he discovered this cathode ray, and also later it was determined that the cathode ray was actually just a stream of electrons. Okay, so what he did was he was able to set up an apparatus, which we'll look at momentarily, where he was able to actually figure out for this cathode ray, as he called it, or what we now know as electrons, he was able to figure out not either the charge on the electrons or the mass, but he was able to figure out what the ratio would have to be of the charge to the mass. So, I mean, that may sound a little bit weird, but there were reasons why he couldn't figure it out all the way down to figuring out what the charge was or the mass, but he figured out what the ratio had to be. And the way that he did that was he made an apparatus that was like the one that I'm drawing this little box around. And we'll see another picture of it in just a second, where he set it up so that there was not only this electric field that we have in this picture, but he also made it so that there was another field called a magnetic field to the sides. And so what he would do is he would start these electrons shooting across this gap like this, and then he would focus it by changing the magnetic field here and here on both sides, and then he would change the electric field, which he had, at 90 degrees to the magnetic field. And he would change the electric field and the magnetic field until the beam would be hitting right in the middle of that electrode. And then he would flip off the magnetic field completely and measure the amount of the deflection on the on the screen over here. This was actually more like a screen here as well as an electrode. So he would measure the deflection and see how far it went, and he was able to use that data to figure out what the ratio was of the charge of an electron to its mass. Let's go to the next slide. So he determined that the ratio of the charge to the mass of an electron was minus 1.76 times 10 to the 8th coulombs per gram, and that's grams of electrons. So all that remained would be for somebody to figure out either what the actual charge was or what the mass of an electron was, which they did. It was actually Rutherford that was the first to do this, and we'll talk about that also. And then what this C right here means, it's also centigrade, so you have to be careful here because it can be used for more than one thing. So here it means coulombs, where 1 coulomb is just defined as a certain number of charge carriers. It's about 6 times 10 to the 18th charge carriers, and charge carriers could be either electrons, and most of the time it's going to be electrons, okay? So it could just be aware it could also be something that has a positive charge. So in this case, he determined that the ratio of the charge to the mass of an electron is minus 1.76 times 10 to the 8th power coulombs per gram of, and that's grams of electrons. Next slide. And then you can stop here and pause and read this if you want to. Let's go to the next slide. So here's a picture of what he actually did. So here's your magnetic field here. Let me draw a little circle around it. So here's the magnetic field, and it's going across from here over on this side to this side. And then you've got your electric field, as you can see here, on the top and on the bottom. So what he would do is he would start the electrons through from the left-hand side, and he would change the electric field and the magnetic field until the electrons were all hitting right there. And then turn off the magnetic field. And when he turned off the magnetic field, this beam would deflect up like this. And that was what allowed him to be able to determine what the ratio is of the charge of an electron to the mass of an electron. Next slide. And then Millikan came along. This again, you'll notice the date here is right after the turn of the century. So much happened at that particular time. Anyway, he came along and he did the oil drop experiment, which you may have heard of or you may not have. And using the oil drop experiment, he was able to figure out what's the charge of an electron. And it turns out that it's 1.6 times 10 to the minus 19th coulomb. So what that is quite profound, because it means every electron has that charge, but it's negative. So for an electron, it's negative 1.6 times 10 to the minus 19th coulombs. And for protons, it's the same number, but it's positive. So this is really an important number right here. So you may have it memorized by the time this class is over. It's 1.6 times 10 to the minus 19th, and that's in coulombs again. And so the way that he did this was he figured out the charge by doing what's called his oil drop experiment, which I'll talk about in a moment. And then knowing this value right here, knowing what the charge is, he could go back to what J.J. Thomson had figured out before, which was this ratio of charge to mass, which I just put the check by here. But in order to figure out the mass, since he had the charge now, he had to flip this number upside down. He had to invert it. Remember, either way, you're just multiplying by 1, so it doesn't matter which one you put on top. So he just flipped it upside down. So he put the 1 gram on top and put the 1.76 times 10 to the 8th coulombs on the bottom. But then he actually went ahead and did the division, but you wouldn't have to. You wouldn't have to, but he did. So, and then also remember there was a negative sign there. There should actually be a negative sign there, I guess. But anyway, so right there should be a negative sign. So when he did the reciprocal, it became minus 5.68 times 10 to the minus 9th, and now it's in grams per coulomb. So he just took and divided 1 divided by 1.76 times 10 to the 8th. And then that got the units right, because now when he multiplies his charge that he just figured out, then when he multiplies that charge here by what we just mentioned about the reciprocal here, the coulombs cancel, and you're left with an answer in grams. So there you go. I mean, this is not particularly difficult. I think I'm making it sound harder than it is. When you multiply the charge times the grams per charge, you get the mass, which is right here. So in other words, he figured out the mass of an electron. The mass of an electron is 9.11 times 10 to the minus 28th grams, which is not something you need to really worry a lot about. In fact, you don't really need to worry about it probably at all. But the charge is important. Again, because as we said, it's the charge on every electron and every proton, and just the sign changes depending on whether it's a proton or an electron. So this number is really important, this 1.6 times 10 to the minus 19th coulombs. It's called the elementary charge because it's the charge on elementary particles like electrons and protons. Let's go now to the next slide. Let's look at how he did this experiment. So here's a picture of, this is a really nice picture. So just very briefly, what he did was he sprayed, and a lot of the experiments they did in this era were just amazingly inventive and clever. So what he did was he sprayed oil drops, which is probably the last thing you think of in conjunction with trying to figure out what's the charge on an electron. But anyway, he sprayed oil drops with a vaporizer over here. So he sprays these oil drops over into a chamber, and below these oil drops there's a plate that's solid except for a tiny little pinhole that's just big enough for 1 oil drop at a time to go through. And that's right here. I'll draw a circle around it right there. So a couple or maybe 3 or 4 of these oil drops would eventually find their way down to that hole and go through it. And as soon as they go through the hole, they start dropping down into this other chamber, and he's got an X-ray machine set up over here that's continually pumping X-rays across this direction so that it hits this pathway that these oil drops would have to follow to come down. When that happens, then it knocks an electron off of the oil droplets. So, I mean, what happens is actually the X-rays ionize the oil droplets one at a time. And in some cases, they might ionize it 2 or even 3 times, so or even 4. So what happens is that every time an oil droplet comes through, it loses 1 or 2 or 3 or 4 or whatever number of electrons. So it becomes +1, +2, +3, +4. And then they applied a potential difference between the top plate and the bottom plate, so that now that these oil droplets are charged, it's like you put a handle on them. And so by varying the voltage here, you can actually cause these oil droplets, because they're so light, you can actually cause them to become suspended here at some point right in the middle, which is what this is for. This is so that this viewer here, so that they can actually watch to see when the oil droplet actually stabilizes. And so they know what the voltage is that they're applying across these 2 terminals here. And so knowing that voltage, they were able to figure out, for example, I mean, let's just do a kind of a imaginary scenario here. Let's say that they got one value that was like 4 times 10 to the minus 19th coulombs, and then they got another value that was 6 times 10 to the minus 19th coulombs, and another one that was 8 times 10 to the minus 19th coulombs, and then another one that was 2. Then what's the lowest of those 4 values, the one that would be the one that would reduce it the most? In other words, the one that would correspond to when you only lose 1 electron. Well, it turned out that that was the one that gave a value for 1.6 times 10 to the minus 19th coulombs for 1 electron. So the one that was about 4 times 10 to the 19th would be about what it would be if you knocked 2 electrons off. 6, I'm rounding this off, okay, so I'm rounding it because it's too hard to follow the analogy if I don't. But if you had 3 electrons, then it would be about 6 times 10 to the minus 19th, and 4 would be about 8, and so forth. So that's what they did, and then what they did was they figured out what's the lowest number here. All right, let's go to the next slide. And I'll let you pause this and look at this. This is an old YouTube link that I don't think works anymore, but I left it here. So you can go on YouTube and look for Millikan's work, his oil drop experiment, and watch a video. This was really a nice video here, but I don't think it's up anymore. But he actually shows like an animation of what was happening. Next slide. All right, so it turns out about this same time also, and completely unrelated to what we were just talking about, is the discovery by different people, including the Curies, of radioactivity. And they discovered, first of all, radium. Becquerel discovered uranium. It discovered that uranium puts out some kind of another mysterious ray, which was kind of like mysterious like the cathode ray. The cathode ray turns out that to be only electrons. The uranium turned out to be putting out a different kind of ray, which is called a gamma ray, and it also was putting out 2 other kinds of radiation, beta decay and also alpha decay. So all of these were coming out and were discovered here by Becquerel in 1896. Then later the Curies started to work with radium, and they discovered that certain things would glow at night, of which one of them was radium. So they would go out at night and look for the stuff that glowed and pick it up out of the ore that it was in naturally, which was called pitchblende. They would wait around in the pitchblende and pick out the glowing parts and then take them home and study them. They didn't realize that they were exposing themselves to dangerous radiation. So if you ever see any pictures of Madame Curie later, when she was in her 40s, she looks like she's about 70, because she's getting zapped constantly while she's waiting around in this stuff and working with it at home. But anyway, so There are three different kinds of radioactivity: alpha decay, beta decay, and gamma decay, which we're going to come back to these later. So let's go ahead and move on and move to something else. And then the last thing we need to talk about here, now we've discovered electrons, we've discovered radioactivity, we figured out the mass, the charge, and the mass charge ratio of an electron. Now, the only thing that remains is what's in the atom besides the electrons. And at first they thought that there were these electrons that were scattered all through these atoms, and then that there were protons that were also going to have to be in there because they would have to have something to balance the charge. So they thought the protons were also just scattered all through the atom, but it turned out that they weren't. It turned out that the protons were all collected together in the middle of the atom, and the electrons go around them like the planets go around the sun. So the way that this was discovered as far as the nucleus is concerned and the protons, and then eventually they realized there had to be something else in there besides the protons, which we now call the neutrons. The way that this was discovered was by the gold foil experiment that Rutherford did. Again, notice the date here is 1911, still around the turn of the century, a lot of stuff going on. And so what he did was he took a gold foil, and if you're not aware of this, like gold has amazing properties. One of them is that you can make a gold wire so thin that it's almost like one atom thick. It's amazingly ductile, and also you can like flatten it out until it's like just incredibly thin. So he did that, made a gold foil that was incredibly thin, and started firing alpha particles. And an alpha particle is just a helium nucleus. Two protons and two neutrons. So he started to fire these things into this gold foil. Now, if the protons were all scattered throughout the gold foil like the electrons, then nothing should have happened. The alpha particles should have all just gone through. But I think he had an intuition that that really wasn't the way it was. So, and his suspicion was confirmed because what happened was when he fired these alpha particles into this gold foil, some of them bounced right back, which shouldn't have happened if the protons were all spread out throughout the entire foil. So they deduced from this that the protons must be gathered together in these large, massive areas that we now call the nucleus. And what was happening was that when the alpha particles hit those nuclei, they would just bounce right back. When they didn't hit it, they just went right through. So most of them went right through, but a few of them would bounce back. Next slide. All right, so now we know, because of all this work that these people did, that there are electrons, protons, and neutrons in an atom. The protons and the neutrons are in the nucleus, and the function primarily of the neutrons is to keep the protons from blowing each other apart, because protons are all positively charged, so they wouldn't stay right next to each other without some way of their charges being neutralized. And the way that they're neutralized has to do with the structure of the protons and the neutrons, which we'll probably talk about that later, so I'm not going to deal with it right now. And then, so you have this nucleus that has protons and neutrons, and then you have electrons that are kind of like, they're not really doing this, but they're kind of like they're orbiting around it. We'll talk more about that later. But just very briefly, the electrons are actually kind of like a wave and a particle, so that they're kind of like a standing wave around the nucleus here, which has to be in certain orbitals. We'll talk about this later. So they have to be either like right here, or they have to be like right here. I'm just planting the seed of this idea in your mind right now. They can't be in between. If they get in between, they immediately have to either snap up here to this position, or they have to snap back down to the lower orbital here. And then there are other orbitals that are available further out. Next slide. So the nucleus was discovered to be very small compared with the rest of the atom, and the usual illustration that I give is that if you went to the old Houston Astrodome, home plate would be like the nucleus, and the Astrodome would be like the size of the atom. Specifically, the atom itself is on the order of angstroms. The nucleus is on the order of femtometers. So you're dealing with a nucleus being 10 to the minus 15th meters, while the atom is 10 to the minus 10th meters. So that's 100,000 times bigger. So most of the space in an atom is made up of the electronic orbitals, and so in other words, it's mostly empty space. Most of the mass, however, comes from the nucleus because the electrons are incredibly light. And just as a rule of thumb, an electron weighs about 1/1000th as much as a proton or a neutron. Next slide. Okay, so here you go. This is nucleus 10 to the minus 15th meters, and then the atom itself is about 10 to the minus 10th meters. That's called an angstrom. So if you are familiar with biology at all, you've probably heard that unit. All right, isotopes is when you have, like, for example, carbon. Carbon would have 6 protons, and that's what makes it carbon. The 6 protons make something carbon. But it can have varying numbers of neutrons. For example, carbon could have either 6 neutrons or it could have more than 6 neutrons. It's still carbon, though, because the thing that makes it carbon is not the number of neutrons, it's the number of protons. So hydrogen is hydrogen because it has 1 proton. But when you have something like carbon that has different numbers of neutrons, even though they're both still carbon, they're not exactly the same because one carbon has more neutrons than the other one. So when we have a situation like that, we call those isotopes. And some things like gold, it always has the same atomic number, which is 79, but it has varying numbers of neutrons. And some atoms can have a whole lot of different numbers of neutrons, so they can have a whole lot of different isotopes. So in nature, as you read at the bottom here, most elements have mixtures of isotopes. So the reason that when you look at the chart and you look at the number of the masses of the different elements, it's not usually an exact number, even for carbon, even though carbon is the basis of our chart, and so everything else is defined from carbon or compared to carbon. So carbon 12 is defined to be exactly 12 units, 12 what we call atomic mass units, where you have 6 protons and 6 neutrons. But if you look at the chart, you don't see under carbon, and you should do this just as an exercise. You look at the chart, find carbon. Well, it's going to have a 6 at the bottom because that's how many protons it has. That's its atomic number. But if you look at the mass number, it isn't exactly 12. It's 12.01. The reason is because some carbon exists not as carbon 12, but there's a little bit of carbon 13 and just a tiny amount of carbon 14. So in order to get that number they put on the chart, they do what's called a weighted average. In other words, they multiply each isotope's percentage in nature by its mass. So for example, if 95% or 98% of carbon is carbon 12, you multiply 0.95 times 12 and then add that to 0.03 times 13 plus 0.001 times 14, and that gives you your weighted average, which turns out to be 12.01. Next slide. So here are 2 isotopes of sodium. So sodium is determined by the fact that there are 11 protons. If you look at the chart, you'll see that its atomic number is 11. But it can have different numbers of neutrons. For example, here on the left, this sodium has 12 neutrons, and on the right, the sodium has 13 neutrons. Both of them are the same thing. They're both sodium because of the 11 protons here. But they're not the same in terms of their actual structure, because this one over here on the right-hand side has 1 more proton than the one on the left, but they're still sodium. So we call those isotopes. This is always on the final exam. They always ask this. So when you have 2 things, they'll either show you the structures or they'll write out the symbols or whatever. They'll just describe it, and they'll say, what is this called? And the answer choices will be like isomers and then some other thing and then isotopes. And so the correct answer will be isotopes. Next slide. So when we write these symbols, this is the way they are in the charts. Sometimes charts, for whatever reason, will invert the A and the Z number. The Z number is the number of protons, so that's what makes whatever it is what it is. Carbon would be 6, so the Z number for carbon would be 6. And so the way that we typically do it in this class is we put this 6 on the bottom and then write where that X is there. That would be C for carbon, it would be H for hydrogen, and so forth. So you would put 6 carbon, and then you would put 12 for where the A is. Here you would put 12, because, or whatever it is, if it is carbon 12, you'd put 12. So this number right here is the number of protons. This number on top, the A number, is the number of protons plus the number of neutrons. So there's no way you can just look at this and see the number of neutrons. You have to calculate that. And the way that you calculate that is you take the A number, which is the number of protons and neutrons, and you subtract the number of protons, or the Z number, and that gives you the number of neutrons. But you can't just look at it and see the number of neutrons. You have to do a quick calculation. Next slide. So let's do a little exercise. A certain isotope, which we're going to call X, don't look in the chart for X, it's not in there. We're just calling it X, kind of like you call X a variable in algebra. So it has 23 protons and 28 neutrons. So what's its mass number? So we just add these together. So the mass number, or the A number, is 23 plus 28, which is 51. And then to identify the element, we go by just the number of protons. So whatever has atomic number 23. Let's go to the next slide. So the mass number is going to be 23 plus 28, which is 51. And then if we look at the chart, we see if we come across to 23 for the Z number that it is vanadium. Next slide. A certain isotope X plus, now here's your clue, has 54 electrons. So you have to be careful here. It has 54 electrons, but it's also got a +1 charge here. So watch this. This is not a neutral atom. So what we need to know is the neutral atom's number of electrons, and that would be 55, because one of the electrons has been taken off, and that's why it has a plus charge here. So it would actually have 55 electrons if it were neutral, which means it would have 55 protons. So we're looking for something that has 55 protons. So what is the mass number? It's going to be the 55 protons. So let me just write P here real quick. And then, so the mass number would be the number of protons plus the number of neutrons, right? So it would be 55, not 54, plus 78, which is 133. Next slide. And so here's your answer. Again, so just pause this if you wish. Next slide. Concept check. Which of the following statements regarding Dalton's atomic theory is still believed to be true? 1, elements are made of tiny particles called atoms. Yes, we still believe that. All atoms of a given element are identical. So think about that for a minute. We just said that we can have what are called isotopes, right? So that means that all atoms of a given element are not necessarily identical. You can have carbon-12 or whatever. Number 3, a given compound always has the same relative numbers and types. In other words, you always have basically a relationship of 2 hydrogens to 1 oxygen for water. So that's true. And then number 4, atoms are indestructible. That's not true. We know that they're made up of smaller parts, neutrons, protons, and electrons, and we know that the atoms can be broken up into those. Next slide. Next slide. Here are our answers. Next slide. Chemical bonds. Next slide. All right, so we have mainly, actually there are several different kinds of bonds, but we're going to worry only mainly about 2 kinds mainly of bonds in this class, of which one of those can be broken up again into 2 parts. But for right now, let's worry about covalent bonds and then ionic bonds. The difference between covalent bonds and ionic bonds is that for ionic bonds, one of the things in the bond, like for example sodium chloride, will give one of its electrons or more up to something else. And then that other thing will become negatively charged, right, because it is an extra electron. And the thing that gave up the electron, like the sodium in this case, would have a plus charge. So now you've got a sodium plus and let's say a chloride minus, and then because they're opposite charges, they attract each other and they actually go together in what's called a lattice. So the difference between an ionic bond and a covalent bond is that in a covalent bond, one of the things is not giving up its electron to the other thing. They're sharing. So when we count the number of electrons around each of the atoms, the ones that they're sharing, we count those as belonging to both. For example, for water, you've got 2 H's bonded to an O, and those are covalent bonds. So they're sharing the electrons. So for the H's, we count the electron that it already had and also the one that it's sharing with the oxygen. And so they're both considered to belong to the hydrogen. And then also that one electron that they're sharing is also considered to belong to the oxygen. So in the case of H2O, you've got an H with, for one of the, or each of the H's, you've got an H with 2 electrons between the H and the O. So those 2 electrons that are between the H and the O are considered to belong to both the H and the O. So you wind up with 8 electrons actually around the O, which we'll come back to later. Let's go to the bottom here where it says that we can also break up covalent bonds again in turn into 2 main parts, and that's polar or nonpolar, which we'll come back to that later. Let's go ahead and go to the next slide. And then ionic bonds, we just talked about this. So if you had calcium and chlorine, the calcium could actually give up 2 electrons, one to one chlorine and one to another chlorine. So now you've got yourself 2 chlorides minus and 1 calcium 2 plus. So you'd have CaCl2. That's the way you would write it, but it actually doesn't form that way. It actually forms as a lattice, as we said before. So it makes like a structured lattice. And so the reason that we call it calcium chloride, CaCl2, is because we just choose out the most basic unit out of that lattice. And I'll let you read the rest of this on your own next. So what we are going to talk about now is the periodic chart. So really we need to look at a chart, and I've got to wait till we get to one, but let me just basically sketch like a real simple-minded periodic chart at the top, and just forget about the irregularities that are usually in there. There's a line across the chart, which I'll show you in a minute when we get to a chart, like right here. And this divides what we call the metals from the non-metals. So everything over here is called a metal, and everything up here in the top right is called a non-metal. So, and then there are also some things here in the middle that are called metalloids, okay, which we'll talk about later also. So whenever you've got a bond between one of the metals and one of the non-metals, you have an ionic bond. And that's the easiest way to remember the difference between ionic and covalent bonds, is that ionic bonds are a metal and a non-metal. So anything from the left side of the chart with the top right side of the chart, that's going to be ionic. And a covalent bond is when you have something that is a non-metal from here with another thing that's a non-metal from here. That's called covalent, and they share electrons. Whereas the ionic ones, actually one thing is going to give up an electron to something else. Okay, so let's go ahead and move on. Here's a picture of what I was just saying. So for sodium chloride, you start off with a sodium atom, which is neutral, and a chlorine atom, which is neutral, but the sodium atom, for various reasons, is willing to give up one of its electrons to the chlorine. So now the chlorine is Cl minus. And if you're worried about why would the sodium do that, we're going to talk about that. It's because of what's called the octet rule, though. It's actually more stable if it gives up an electron, and the chlorine is actually more stable if it gains an electron. The sodium here is a metal. It's on the left side of the chart if you want to look at a chart. If you have a chart handy, grab it. Look up sodium. It's in the first column on the left, and chlorine is in the 7th column on the right, top right, so it is a non-metal. So we've got ourselves here a metal and a non-metal, and when they come together, they make ionic bonds. And they don't make molecules. They make these things right here, and these things right here are called lattices. So in the lattice here, you've got a whole bunch of these purple spheres, which are the sodiums, and you've got a whole bunch of the green ones, which are the chlorides. Okay, so they go in plus, minus, as you can see there. So instead of trying to name this whole thing, since they vary in size, we just take the basic unit, which I'm drawing a box around right now. So that's 1 sodium and 1 chlorine when they've bonded. And we call that not a molecule, but we call it a formula unit. And of course, this is just table salt, as you see over here on the right. Next slide. And then there are other types of bonds that are between like molecules. And so when you have a covalent situation like water, you've got a covalent bond between the H's and the O's in water. So you actually have distinct molecules, whereas not like what we just looked at with the ionic bonds, where you have these lattices. You actually have molecules, and they're separate from the other molecules. but you can still have forces between the molecules, and that's what this is talking about. There are actually 4 of those, and we'll talk about those later in the class, so let's go ahead and move on. So let's go to the table, and now I can kind of pick up on what, let me actually go to the next slide here, and let's just look at this. Now this is super important. This is the most important thing I'm going to talk about today other than naming. Here is the line I was talking about, just like that. It's a zigzag line, and on the right and above this line, these things over here are the nonmetals, and the things on the left are called metals. All of these. So you say, well, that's not really fair, right? Because there's more metals, but that's just the way it is. Now, one other thing that may have occurred to you is if we have one kind of bond between metals and nonmetals, which we called ionic, and we have another kind of bond between 2 nonmetals, which we call covalent, shouldn't it be fair that we would have a bond between 2 metals? And the answer is usually, I mean, basically never will that happen, because there's not really any mechanism for 2 things to get positive charges and then bond to each other. All right, so we're going to talk about naming, and we're also going to talk about how things come together to make bonds. So let's look very briefly here. Things over here, okay, so notice if we don't worry right now about this box that I'm drawing a line around right now. Let's just forget about this for right now. Let's only worry about the first 2 columns over here and the last 6 over here. So we have a total of 2 plus 6 is 8 columns. It turns out that the things in that very last column where I'm drawing the arrow, the 8th column over here, this column, are very stable. And the reason they're very stable is because there's something about the way atoms are constructed that if they have 8 electrons, and again, we're just talking about the things here in the groups that I just mentioned. If they have 8 electrons in their outer shell, they're stable. For whatever reason, which it deals with quantum mechanics, which we won't get into that, just remember that for our purposes right now, everything wants to have 8 electrons in its outer shell. Now there's an exception to that, or 2 exceptions to that, actually 3, and that's hydrogen, helium, and then also lithium and beryllium over here. They can't get an octet, but they can settle for the next best thing, which is called a duet. And a duet is when they have 2 electrons, like helium. So, but except for those few exceptions there, everything else here in the main group, we call that the main group elements. The first 2 columns and the last 6 columns wants to have 8 electrons. And so they'll enter into reactions in order to get 8 electrons, which is what we just saw with sodium chloride. Sodium has 1 extra one. So the way that you count the number of electrons that are in the outermost shell of an atom, and we call that outermost shell the valence shell, is you just count what column is it in. So this, we're going to call this the first column, the second column, and then we skip all of this stuff in the middle. So just skip this stuff, and then come over here to boron. That's 3. Carbon here would be 4. Nitrogen would be 5. Oxygen 6. And you can see the numbers down here also, where the A numbers are, and then this would be 7. So the ones over in the 8th column here are happy. So they don't really react. I mean, you can make them react, but it's kind of like an extreme situation. Most of the time they don't react at all. So things like helium, neon, argon, krypton, xenon, radon, and those sort of things will not react under ordinary circumstances because they're happy. So we call that 8th column, or group, is called the noble gases. There are other names for them as well. So these things represent the stable state. So what everything else in columns 1 through 7 is trying to do is get to that stable, happy state that the things that have 8 electrons enjoy. Okay, so everything in the first column has 1 valence electron, as we said before. And so it turns out that it's easier for the lithium or the sodium or the potassium, it's easier for them to attain an octet by losing 1 electron. What that means is that, for example, for sodium here, which I'm circling, if it loses 1, then its electronic structure will actually revert back to this right here, because it now has only 10 electrons because it lost 1. So sodium plus has 10 electrons, not 11, as it would have had in the neutral atom. So like if you have sodium, if you have like for example a sample of sodium, it looks kind of like a loaf of bread. It's a metal, and it's an atom and it's neutral. But if you react that sodium with chlorine, the sodium will give up one of its electrons, which will cause it to have the valence shell electronic configuration of neon. In other words, it will be stable. So what I'm suggesting is that sodium plus is happy. It's happy. So in other words, what I'm saying is that sodium atoms will give up one electron because they're happier without it. And I won't make any jokes at this point. So sodium will give up an electron. On the other hand, let's say chlorine here, which that was the other thing we talked about, has 1, 2, 3, 4, 5. So start from the left and count across. It's 1, 2, and then over here is 3, 4, 5, 6, 7 valence electrons for chlorine, right? Because it's in the 7th column. It has 7 valence electrons. How many does it want? Well, think back to what we said a minute ago. It wants how many? 8. How many does it have? 7. So it needs one more to be really happy. So if it takes this electron that sodium just gave to it, then it will have 8. So it will also have the same electronic configuration, as we call it, as a noble gas, in this case argon. Okay, so I think we've said about enough of this. So the way that we are going to do this is we're going to say that everything over here on the top right is going to make a covalent bond if it bonds to something else in the same area. In other words, in the nonmetal or the top right area. And an ionic bond if it bonds to something over here on this part of the chart. That's an ionic bond. When you have a metal and a nonmetal. It turns out when we name them, we're actually going to divide that part over here on the left that I just indicated into the ones that are over here and what we call the main group elements, the first 2 columns, and also a few of them over here, like aluminum and so forth. So maybe a few more down here on this side. And then the ones in the middle we're going to name differently for reasons that we'll talk about in just a moment. Okay, and then the things in the middle here, just very briefly, where this zigzag line is, are called metalloids. And some of those are also semiconductors, so we'll talk about that later, so I don't want to waste any time on it right now. So let's go ahead and go on. Next slide. All right, so we have 7 elements that basically, if they're in the gas phase, they occur as diatomic molecules, which we talked about this before in Chapter 1. Hydrogen, nitrogen, oxygen, fluorine, and chlorine are gases at room temperature, so they will be diatomic. And the reason is because of the same thing we just mentioned, which, by the way, is called the octet rule, where everything is trying to get an octet in its outer shell of electrons. In other words, everything's trying to get 8 electrons in its outer shell, except the exception here would be hydrogen because it can't take 8. It's not big enough. So it tries to get 2, remember? So we call that the duet rule. The other ones, nitrogen, oxygen, fluorine, chlorine, won't exist in the atmosphere. They won't be floating around as N here and O here. It will be N2. And you'll have to remember that because a lot of the problems depend on your being able to identify these correctly. So if you have air, then there's a lot of nitrogen in the air. It's mostly nitrogen. 79% of air is nitrogen, but it isn't N, it's N2, okay? The reason that it goes to N2 is because N2 is more stable. It's happier being N2 than it is as just N, because N has 5 valence electrons, but if it comes together as N2 for various reasons that we'll talk about later, it can make an octet for both the N's. So they both have an octet, so they're happy. And then also, if you heat bromine or iodine up until they become gases, then they'll also form diatomic molecules. They're not gases at room temperature. Next slide. Here's another picture which is kind of like illustrating what we talked about before. So notice here, I'm drawing an arrow here above the first column or group. Notice that everything in that column or group has a +1 charge because everything in that group is going to give up 1 electron. Remember, you count across the number of columns, so the first column would be 1. So that means it has 1 electron in its valence shell, and it doesn't want that. It wants 8. So it's either going to have to gain 7 or it's going to have to lose 1, and it's easier to lose 1. The second column, it's easier for it to lose 2. The third column, it's easier to lose 3, and that's basically aluminum. The fourth column doesn't really, we don't have it in here because it can go either way. And that's something like carbon or sulfur below it. Nitrogen in the fifth column has 5 valence electrons, so it's easier for it to just take 3 more than to lose 5. So if it takes 3 more, it will have 3 extra electrons, so it has a 3 minus charge. Oxygen, it's easier for it to gain 2 than to lose 6. If it does gain 2, it will have a 2 minus charge. Fluorine and everything else in the 7th column here. Sorry, let me go back over and make a correction. Okay. Everything in the 7th column is going to have 7 electrons in its valence shell. And it wants 8, so it will take 1 more, which will give it a -1 charge. Let's go to the next slide. So the first column or group is called the alkaline metals. The second column is called the alkaline earth metals. The 7th column is called halogens, and the 8th column is called the noble gases or the inert gases. So you should try to remember these names. And also remember that the things in the first column or group will be +1. The things in the second column will be +2. In the 7th column, they want 1 more electron, so they'll be -1. And the 8th column will not do anything, so they are going to be 0. Next slide. So let's go into naming. So we're going to find that there are 3 different ways you can name things. Basically, one way would be if you have a metal and a non-metal, which means you have an ionic bond. And then the other main way is if you have 2 nonmetals, which is a covalent bond. So when you have 2 nonmetals, you name them differently. Like if you have a carbon and a nitrogen together, you don't name it the same way as you do ionic bonds. When you have ionic bonds, you have 2 different possibilities. So let's just go to the next slide. And let's go to the next slide. Next. Okay, so when you have an ionic bond, there are 2 different ways it can happen. It can either be between a main group metal and a non-metal, or it can be between a transition metal. Now, the transition metals are the ones that were kind of the light brown color that we looked at before, the ones in the middle of the chart that I drew the box around. And I said we're not going to worry about those right now, but we are going to worry about them just in terms of how to name them. So when it's a transition metal, basically you have to name it a little bit differently than you do if it's just an ordinary main group metal. So if it's an ordinary main group metal, something from column 1, 2, or 3, and it's making an ionic bond, we call that type 1. And if it's from the transition metals bonding to a nonmetal, we call that type 2. And if it's 2 nonmetals, then we call that type 3. Okay, so each one is just a little bit different. So the main rule is that you call the cation, like for example, the sodium chloride would be, the sodium would be the cation because it's going to become plus. So you name that first and you just name it. You don't change it. So it's just sodium or calcium or whatever. Then the anion would be basically the same thing. So for sodium and chlorine, it would be sodium chlorine, except you just make a slight change and you call it sodium chloride. Potassium bromide, silver chloride, silver iodide. Okay, so you just change the N or whatever to a D. So that's called type 1, and that's all you have to do. That's all you have to do. These are the easiest ones. Okay, let's go to the next slide. So here are some examples. The KCl, potassium, doesn't change, and then chlorine changes to chloride. Bromine here in the second example here changes to bromide. Oxygen changes to oxide. So you're actually changing the word up a little bit for oxygen. It's not going to be a problem. It'll come to you very easily, hopefully. So CaO, Ca is calcium, so it's calcium oxide. Next slide. The situation you can sometimes have is when you have one thing that has like a +2 charge, like something from the second column, and it's bonding together with something from the fifth column, like nitrogen, that has a -3, then the way that you know how many numbers to put or what numbers to put here and here is you just transpose the charges. So put the 3 here and put the 2 here. So you have Mg3N2. Now, that doesn't come up that much, but it does come up. Okay, next chart, next slide. Okay, type 2. Type 2 is different slightly from type 1, and the difference is that for type 2, you put in what's called an oxidation state number to show what oxidation state it is. And don't worry if you don't understand what I mean by that right now, because it'll come to you. So type 2 is mostly, but not completely, but mostly the transition elements, the things in the middle of the chart. So for example, things in the middle of the chart that we looked at earlier can have typically more than one possible oxidation state. So what do I mean by oxidation state? Well, remember we said that things in the first column, like sodium, have 1 valence electron. They don't want 1, they want 8. So it's easier for them just to give up 1 than it is to gain 7. So if they give up the 1, what's the charge going to be on a sodium? It's going to be +1. So its oxidation number, or its oxidation state, is +1. Okay, so, but it turns out that the things in the middle, the transition metals, can have, in most cases, more than one possible way they can do this, because they're more complicated. They have more subshells. They have D subshells. So they can have different combinations of making molecules, so they can take more than one oxidation state. So we have to indicate which oxidation state we're dealing with in that particular variation of that transition metal. Also, tin and lead are also in this category, even though they're not transition metals, but they also can take either a +2 or a +4. So they're main group elements, but we still have to put a Roman numeral for tin and lead because they have more than one possible way that they can make bonds. And then also, there are some other things like in the transition metals that, even though they're transition metals, they can only take one oxidation state. So most of them, the majority of the transition metals, I mean, I might say the vast majority, can take more than one. So you have to write the Roman numeral. There are actually 6 of them out of all of them. There's a bunch of them. 6 of those that can only take one oxidation state. So it isn't really incorrect to write the Roman numeral after them. And you'll see what I'm talking about the Roman numeral in a moment. But you don't have to write it because everybody understands. And an example of that would be silver. So even though silver is in that middle part of the chart, which we call the transition metals, it's a transition metal, so it should have a Roman numeral when we name it, but it doesn't. Typically people don't write it because it's understood that it has to be 1 because it's always 1. So let's go to the next slide. So when we name type 2, and remember that's basically transition metals with nonmetals, okay? When we name these, we name them the same way we did the type 1, except for one thing, and that is that we have to put a Roman numeral after the first thing in the formula, or in the name. So let's go to the next slide. So for example, here we've got copper bromide. And in this case, if you look at the chart, you'll see that the copper is in the transition metals. So it can take more than one possible oxidation state. In this case, it's taking +1. And the reason we know that is because bromine is in the 7th column. It has 7 valence electrons. So we know that the bromide is going to be -1. And so because this is a neutral molecule, the copper here has to be +1. So out of the different possible states that copper could have here, we know this one is 1. So we write 1 after the copper. Now there's no space, you'll notice here, and that's not a typo. That's the way it's supposed to be. And why it's that way, I have no idea, unless they're trying to make it all like one name together here. So the difference between type 1 and type 2 would be, if it were type 1, you would just say it's copper bromide. But for type 2, which we have to use here, because copper can take more than just the +1, it can take other possible states, then we have to write which one it's taking in this particular molecule, or formula unit. So we write copper, open parentheses, Roman numeral 1, and then close parentheses, bromide. So the difference between type 1 and type 2 is just that Roman numeral. For iron, iron is another transition metal. In this case, it would have to be +2 because the sulfur's in the 6th column, so it's going to be -2, or it's usually written as 2 minus. And again, I don't know why. But anyway, that means that the Fe here has to be 2 plus to match it because there's no charge on it. It's neutral. So if you got a 2 minus here, then you have to have a 2 plus here. So that means that we have to write a Roman numeral 2 here after the iron. So it's not iron sulfide, it's iron 2 sulfide. For lead, this is one of the two that I mentioned previously that are not transition metals, but you still have to do the Roman numeral because the lead and the tin can both take +2 or +4. In this case, this has to be +4, and the reason we know that is because we know O is -2, so this has to be +4. The O's are always -2, basically, with a few exceptions, which we won't worry about right now, because they're in the 6th column. They have 6 valence electrons, so they want 2 more, and if they take 2 more, they're -2. But we have 2 of them. So 2 times -2 is -4, so the O's are -4 total, which means that the lead has to be +4. So we have to write a Roman numeral 4 after lead, after the word lead. So it's not lead oxide, it's lead 4 oxide. Next slide. So here are the here is like a summary of the different columns. So these would be column 1 or group 1. Remember, we said that they're actually given the technical name alkali metals. Column 2 or group 2 would be the alkaline earth metals. And then here are the charges. You'll notice that everything in the first column is +1, right? Everything that I just drew the line by, and here everything is +2, and here everything is +3. There's only one thing in there, but still. So these are the different kinds of states. Now notice here that, actually, maybe it would be a good idea if you just kind of like don't worry about this part for right now. Let's go to the next slide. And then on the other side, the things that I'm drawing the line beside right now are called halogens. F, ClBr, and I, they have 7 valence electrons. They want 8. If they take 1 more to get 8, they have a -1 charge. Things in the 6th column have 6 valence electrons. Don't worry about the one here. Let me make an X by this. Just don't worry about this for right now because it'll just confuse you. The O and the S are in the 6th column. They have 6 valence electrons. They want 8, so they take 2 more. If they do take 2 more, they have a -2. Nitrogen is in the 5th column here, the one that I'm marking. So it has 5 valence electrons. It wants 8. If it takes 3 more to get 8, it will have a -3 charge. Again, don't worry about this stuff over here right now. We'll get to that later. Next. All right, so now we need to talk about one other thing in terms of naming, and then there's also one other thing after this, and that's acids. So anyway, we're kind of approaching the end here, so don't panic because there's not that much more. Okay, polyatomic ions are things that have special names. That's all they are. So instead of trying to name some things, because there are so many, like if you'll look here at the second and third example, this one right here, it didn't work. That one right there and this one right here. Look how much stuff there is in there that you'd have to try to name. So to make it easier, there are certain groups that are given special names for just the whole group. Like for example here, this thing right here is just called hydroxide. So instead of trying to call it sodium, oxygen, hydrogen, and I get that on tests a lot, somebody will be trying to name this, and the name of this is just sodium hydroxide. It's just the sodium, and then that part right there is just called hydroxide. Sometimes people will try to call it sodium, oxygen, hydrogen, or whatever. So don't do that. So you just memorize these special groups. So OH minus is called hydroxide, NO3 minus is called nitrate, and NH4 plus is called ammonium, not ammonia, ammonium, and SO4 2 minus is called sulfate. So those 4 things right there you should definitely memorize. So what I'll do is there's actually more than just these 4. So what I'll do is I'll in just a moment show you a chart which has a lot of these on them that are called polyatomic ions. And poly means it's from the Greek. It just means many atoms. So in other words, for example, here NH4 has like an N and 4 H's in it. So it's just named as one thing. it's called ammonium. So you don't have to say nitrogen tetrahydride or whatever. You just say ammonium. Let's go to the next slide. All right, here's a chart, and what I'm going to do is I'm going to go through here and mark the ones that I think you should start learning now at the beginning of the semester. So everything that I'm drawing a line next to, and I'll name them in just a moment, are the things that I want you to try to learn now. And I don't want to make this too hard, so I'm not going to mark everything that you'll need to know for the rest of the semester. I'm just going to name the ones that you need to know for like right now. And some of them, you may look at it and say, why is he marking that one? Because that looks hard. But the reason is because they're going to be things that we do on the work problems. So let's just take this. So I've marked NH4 plus. Let me just count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 11 here. So it isn't that hard. But start with these. At some point during the semester, though, before the final, certainly, you'll want to probably try to remember every one of these, but just take it easy. Just take it a little bit at a time as your brain will be able to absorb it. If you try to cram all of these in at once, it's hard, and you're just going to forget them anyway. So start off with the ones that I have marked. So that's ammonium nitrite and nitrate. Notice the only difference between those is that letter I or A. Same thing for the sulfide and the sulfate. And then hydroxide, phosphate, carbonate, permanganate, chromate, and dichromate. Okay, so let's go back through these one at a time very briefly. For ammonium, it's NH4 plus, and it's not ammonia, it's ammonium. So the difference is that NH3 is ammonia, like you use around the house to clean. The difference between nitrite and nitrate is that the nitrite has 2 O's, and the nitrate has 3. Notice they both have the same charge, though. They both have a -1 charge. The difference between sulfide and sulfate is, again, the number of O's. But in this case, because S is in the third row, it can accommodate more O's because it's a bigger atom. So in the case of sulfur, it can take 3 or 4. And so when it takes 3, it will be called sulfite. So the ITE ending goes on the one that has the lower number of O's. And the ATE ending goes on the one that has more O's. Now we're going to come back to this when we talk about acids, so let's just touch on it right now. Whenever you have a nitrite and it becomes an acid by adding an H to it, and we'll see this again later, but we call it nitrous acid. And when you have nitrate, where you have an NO3 minus that takes an H, it becomes nitric acid. Okay, so that's just to plant the idea in your mind. We'll come back to that later. Hydroxide is OH minus. Phosphate is PO4 3 minus. And you also need these charges. You have to know what the charges are in order to be able to do most of the problems. Carbonate is 2 minus, CO3 2 minus. If you add 3H, well, it's, okay, let's come back to that later. Okay, MnO4 minus is permanganate. CR2, actually, let's do the one below it. CrO4 2 minus is chromate, and CR2O7 2 minus is dichromate. Those are the ones you should start off with, and if there's anything else, I'll tell you when we get to it. Next slide. So whenever you've got something that has the O's, like the nitrite, nitrate, sulfite, sulfate, as I said before, the one that has the fewer oxygens, you call it ite. The one that has more, you call it ate. Now, just to go back to this, N is in the second row, so it's a smaller atom than S, which is in the third row. Every time you drop down a row, the atoms get bigger. So N is not as big as S, so we can only accommodate a maximum of 3 O's because it's just not big enough to take more. Whereas the sulfur can accommodate 4. So the numbers that I've written over here on the right-hand side are the rows that these things are in the chart. So when you have nitrogen, it can take a maximum of 3 oxygens. If it does do that, it's called nitrate. If it takes one less than that, it's called nitrite, NO2. Notice again, they both have a -1 charge. The sulfur things both have a -2 charge. And the one that has the maximum number of oxygens is going to be SO4, and that's called sulfate. And the one that has fewer is called sulfite. And you can actually take this even further. Some things can actually go one more than the sulfate or the 8, and some things can go one less than the 8, and then some things can actually do both. Now, chlorine can actually do both, so we have a special way of naming that, but you don't have to worry about that with nitrogen or sulfur. And then again, I'm going to go ahead and talk about this now so it'll be easier for you when we get to it. If I added an H to NO2 minus, an H plus to that to make it HNO2, we would call that nitrous acid. But if I add an H to this one, we call it nitric acid. H plus, sorry. If I add H plus to this, we have, actually it would have to be 2 of them in that case. We would have sulfurous acid, and if we add 2 H pluses to this to match the 2 minuses, we would have sulfuric acid. Next slide. Okay, the chlorine. Let's go ahead and move to the next slide. All right, and then as we said a moment ago, I won't spend a lot of time on this because we're going kind of like long here. But for chlorine, you can not only have the chloride and the chlorate, but you can also have one that has 4 oxygens here. So this one is going to be one of the ones that can take a maximum of 4 oxygens, but you don't call that one the chloric or the chlorate. You call this one actually a different name. So these two in the middle would correspond to nitrite, nitrate, sulfate, chlorite, chlorate. But in the case of chlorine, it can also take the case where there's only 1 O, which is all the way over here to the right, or it can also take the case where there are 4. So you have to have a special way to name these. And you're probably not going to see this very much, but just so you'll be aware of it, you call the one that only has 1 O, in this case when you have 4, hypo. You put that hypo in front of chlorite. This one is chlorite, this one is chlorate. So this is like the nitrite and the nitrate. And then when you get to the one that has 4, you put PER, per, in front of the chlorate. So this is chlorate to perchlorate, and this is chlorite to hypochlorite. And again, notice the charges on all 4 of these are all the same. So try to remember that. The charges are not changing here. Even though we're changing the number of O's, we're not changing the charge. All right, next slide. Next slide. And then type 3, and I'm going to go ahead and wrap this up because we're going kind of long here. So we're just going to have to finish this up, and we don't have that much more to go anyway. So type 3 is when you have 2 nonmetals. So the difference between this one and the other ones is, first of all, it's covalent. Secondly, it's between 2 nonmetals. And then when you name them, the difference is that you use prefixes. Like, for example, 2 becomes di, 3 becomes tri, and so forth. 4 becomes tetra. So, for example, if I have NO2, N and O are both nonmetals, so that's a covalent bond. So I call that nitrogen dioxide. If I have CO2, I call it carbon dioxide. If I have CO, I call it carbon monoxide, where the mono means 1. Now you'll notice on all of this that I didn't put mono in front of the carbon or the nitrogen, and the reason is because for the first word in the name, you don't have to put mono. It's assumed that unless you put di or tri, it's assumed to be mono. Next slide. So here are the prefixes. Mono is 1, di is 2, tri is 3, and so forth. Next slide. So carbon with 2 oxygens is called carbon, not carbon oxide, but carbon dioxide. Sulfur with 6 X's is called sulfur hexafluoride, not fluoride, but hexafluoride. So you have to look at the chart until you get to the point where you memorize these to see where they are, to see how you name them. In this case, you do put the di in front of the nitrogen here because you've got not 1 but 2 things in the first part here. So you do have to put di-nitrogen, and you still have to put tetra oxide, but they changed that from tetraoxide to just tetroxide. Next slide. Acids, we've already talked about this, so let's go on and finish it. So usually, but not always, you can recognize acids by the H's. Next slide. So some of these are not too bad. Like, for example, if you have HCl, it's just called hydrochloric acid. So you're just adding an IC at the end of the hydrogen chloride. You're changing the chloride to chloric, and then you put the word acid at the end always. So HCl is hydrochloric acid, HBr is hydrobromic acid, HI is hydroiodic acid. HCN is hydrocyanic acid, cyanic acid, and that is because this is one of the polyatomic acids, one of the polyatomic ions that we were talking about earlier, but we didn't actually list this one, but this one is in that list. So Cn minus is cyanide, so we change the cyanide to cyanic and add the word acid. H2S is just, instead of hydrogen sulfide, is hydrosulfuric acid. It doesn't matter that there are two H's there. Next slide. So when, as I said before, when you have O's on the acid, then if it's the one that has the fewer number of O's, you call it nitrous or sulfurous or chlorous. So these correspond to the nitrite, the sulfite, and the chlorite. The next slide is going to show us what happens if you have the maximum number of O's. Let's go to that. Oh, and then here's another chart of the ions. So I just put this in here so you could look at these and remember the names. Next slide. When you have the maximum number of O's, for example, if you have 3 O's by an N, that's as many as it can take. That would be nitrate, but if it's an acid, it's called nitric acid. SO4 2- would be sulfate, but if it's put into an acid, H2SO4 becomes sulfuric acid. The reason you have to have two H's is because SO4 has a 2- charge. And then this one right here, you'll just maybe want to remember this. CH3COOH is called acetic acid. Next slide. And then here is a list that at some point you're going to want to remember these. So why don't you start right now by just remembering that HCl, HBr, and HI. Now, the Cl, the Br, and the I are all in the 7th column. They're all halogens. And when they make acids, they're strong acids. There are only 7 acids out of all the acids in the wide world, and there's a bunch of them. Only 7 of them are what we call strong acids, and let's don't get into that anymore right now. And for various reasons, we're going to need to memorize these at some point. And then try to remember that HNO3 is nitric acid. We just said that on the previous slides. And H2SO4 is sulfuric acid. And then these last two here we'll get back to later, or you can get back to later. Next slide. So let's quickly do this because I'm out of time. Which of the following is named incorrectly? So A is KNO3, that's potassium nitrate. And the name is potassium nitrate, so that's correct. So let's put a check. Ti is titanium. O is -2, but there's 2 of them, so that's -4. So that would have to be +4. And it isn't, it's +2. So let's leave that. This one is going to be tin hydroxide, and it would have to be, each one of these OH is an OH minus here, and there's 4 of them. So that's -4 total for this part of the molecule. So the tin, the SN, which the abbreviation for tin is SN, that comes from stannous. The tin would have to be +4, and it is, so this one is correct. This would be phosphorus pentabromide, and that's correct. And then that last one, that CrO4 thing, was CrO4 2-, which was one of the ones I asked you to remember, and that's chromate. So that's just calcium chromate. So you just name that last part there as just chromate, just one word. And that's right. So the one that wasn't right was this one right here. This should be titanium 4 oxide. Let's go to the next slide. Next. And so there is the correct answer. Next slide. All right, so we're done with this right at an hour and a half. That's as long as I want to go on any of these videos. So let's stop here, and I'll see you in the Chapter 2 work problems.